So electric flux is useful because we can actually calculate the electric flux of any given particle or series of particles, and we're going to do that later on. So imagine that we, for instance, define, well, there is an area, right? And it is at a distance r of this particle. So if I want to actually analyze what is the electric flux in a small piece of area, well, there is going to be a differential of area, that is a small piece of area, and well, there is this particle is going to emit an electric flux towards this direction, right? So for instance, for the particle, the differential of electric flux is going to be equal to the electric field in a dot product with the differential of area. In this case, since they are totally parallel, well, the cosine of the angle is 0, and this will give me the magnitude of electric field times the differential of area. And if I add up all of the electric fields of the whole sphere that is surrounding this particle, well, we can actually see that that is all the electric flux at that area, and well, this is equal to an integral. Which integral? Well, the sum of all the contributions. Just remember that since this is an scalar, you can add, for instance, all the contributions. The total electric flux is going to be equal, for instance, to all of the contributions, right? As scalars, or as apples, or as oranges, etc. But if we are working with small pieces, then I am going to do the integral of all the surface of this EDA, and this will give me the sum of these contributions, all of the contributions of small pieces that this surface, which is imaginary, has. Now, in this case, for instance, if the electric flux is constant, and it will be constant because we are evaluating the electric flux at different points of R, well, this can go out from the integral, and the integral of surface of the differential of area is the area per se. And since this is an sphere, the area is going to be, for instance, 4pi r squared. This is going to be then the electric flux. And since the electric field we know already for this particle is, for instance, kq over r squared times 4pi r squared, well, r squared can cancel, and this will be, for instance, kq times 4p. And if we look for the definition of k, the actual definition of k, well, it's, for instance, k is, for instance, 1 over 4p epsilon 0, being epsilon 0 a constant as well, and this constant is, for instance, called the permittivity of free space, and this is an electric constant. So, for instance, here we can cancel 4p with 4p, and we can actually get a relationship that states that the electric flux is given by the charge which is enclosed. Other charges will actually cancel over epsilon 0, enclosed in a surface. So this surface that is imaginary is called a Gaussian surface. And this Gaussian surface will determine which is the charges that are enclosed. So at the very end, what we will have is that the integral of surface, I am going to put a surface like this, of E dot dA, which is the electric flux, is going to be equal to the charge enclosed over epsilon zero. This is called, for instance, Gauss's law.